Welcome to this explainer. Right now, hiding just beyond the limits of our human sight, there are incredibly sophisticated microscopic chemical teams operating all around us. They're working silently, inside the leaves on the trees outside your window, literally catching sunlight. They're actively pumping through the blood in our veins, keeping us alive second by second. For a long time, the exact mechanics behind these everyday miracles were completely hidden. But today, we're going to uncover exactly how these secret chemical super teams are structured, how they operate, and honestly, how they essentially run the natural world.
So, have you ever stopped to wonder what exactly gives grass its bright, vibrant green color? Or, for that matter, why our blood is so brilliantly, unmistakably red? We kind of take these fundamental, everyday colors totally for granted, right? When asked, most of us just chalk it up to basic biology and move on. We'll say, oh, it's just chlorophyll, or it's just hemoglobin, without really thinking about what that actually means on a structural level. But the truth is rooted in some incredibly elegant, highly organized chemistry. Let's dive right into this and look closely at the actual molecular machinery responsible for these everyday visual miracles.
The answer to our color question lies in special, highly organized molecular superteams called coordination compounds. In modern inorganic chemistry, a coordination compound, or sometimes it's called a coordination entity, is defined as a central metal atom, or ion, that's bonded to a fixed number of surrounding islands or molecules. Essentially, you've got a heavy metal atom sitting right in the dead center, acting as the anchor. It shares its electrons with a very specific, dedicated group of chemical companions clustered tightly around it. And they don't act as separate floating pieces. No. They act as a single, unified team working together to accomplish things that the individual parts could literally never do on their own.
To make this complex structure a bit easier to picture, think of it like throwing the ultimate molecular party. In this scenario, the central metal atom, which chemically speaking acts as a Lewis acid, is the host of our party. The surrounding molecules or ions are the invited guests, which chemists formally call ligands. Now, the guest list at these parties can vary wildly. These ligands can be tiny, simple ions like chloride, just pulling up to the party alone. They can be small molecules like water or ammonia, or they can be massive, sprawling macromolecules like complex proteins taking up a huge amount of space. But regardless of their size, they all gather around the central host in a highly specific, geometric arrangement.
Now, understanding the rules of this molecular party wasn't always so clear-cut. Back in 1898, a Swiss chemist named Alfred Werner essentially cracked the code. And let me tell you, it was a massive breakthrough for chemistry. Before Werner, the way these metals bonded seemed almost chaotic. But Werner proposed that metal hosts actually have two distinct types of connections, or valences. The first is the primary valence. Think of these as the flexible, ionizable connections usually satisfied by negative ions just kind of hanging around the periphery. But then, crucially, there's the secondary valence. These are non-ionizable and rigidly fixed in number. Imagine it as a strictly locked number of VIP seats right at the host's table. A metal host might have exactly 4 or exactly 6 VIP seats available, and this dictates exactly how many guests the metal can directly bond with. This secondary valence is what we now call the coordination number.
And depending on who actually sits in those VIP seats, we get entirely different types of gatherings. Sometimes the host throws an exclusive, highly uniform party. We call this a homoleptic complex. This is when the metal host is bound to only one single kind of guest. Imagine a cobalt ion surrounded exclusively by 6 ammonia molecules. Because of the way they repel each other, they'll naturally arrange themselves into a perfect geometric shape, like an octahedron, right around the host. But other times, it's a heteroleptic mixer. That's when the metal is bound to more than one kind of donor group, so maybe 4 ammonias and 2 chlorides hanging out together. The cool thing is, even with a mixed crowd of guests, they still snap into incredibly precise shapes, whether that's an octahedron, a tetrahedron, or a flat square, all depending on that coordination number.
So with all these different guests, party types, and geometric shapes, you can imagine how quickly things could spiral into absolute chaos, right? Without a strict VIP list, chemists would have a nearly impossible time communicating exactly which complex team they were studying. To solve this, the International Union of Pure and Applied Chemistry, or IUPAC, created specific universal naming rules so there's zero ambiguity worldwide. First, all ligands are listed strictly alphabetically as prefixes, completely regardless of their charge. Next, if a guest is an anion, its name gets a rather cool formal suffix tweak, ending in ido, so a standard chloro guest officially becomes chlorido on the VIP list. And finally, the central host's oxidation state, which is its electrical charge, is probably displayed in Roman numerals right at the very end of the compound's official name.
Now, here's where it gets really interesting. Even if you have the exact same chemical formula, meaning the absolute exact same total number of hosts and guests in the beaker, you can completely change the party's vibe through a concept called isomerism. And this is absolutely crucial because it's not just a fun trivia fact. Swapping a guest can completely change a compound's physical color, its reactivity, or even whether it acts as a life-saving medicine or a highly toxic substance. For example, in coordination isomerism, ligands literally swap places between two different metal hosts. Imagine ammonia guests leaving a chromium host to go hang out with a cobalt host instead. Then there's ionization isomerism, where a guest currently bound directly to the metal swaps places with an outside counterion that was just waiting in the surrounding solution. It's the exact same pieces, but entirely different, highly consequential chemical properties.
All right, let's move into Section 1, the science of color, and look at these flashy outfits.
So why are these compounds so famously colorful? This brings us to a beautiful concept called crystal field theory. Let's imagine shining a white flashlight at a titanium complex in a solution. White light, as a prism shows us, contains all the colors of the rainbow. When that light hits our metal host, a single electron sitting down in a lower energy orbital, which is known as the T2G level, absorbs a very specific wavelength of that light. Let's say it absorbs the energy of the blue-green region. Powered up by that energy, this electron gets super excited and does a massive energetic jump up to an empty, higher energy level called the EG level. Because the complex absorbed the blue-green light to make this jump happen, the blue-green light doesn't pass through. Instead, the remaining light that bounces back to our eyes is the complementary color. In this specific case, it appears as a stunning, vivid violet. It's literally the physical movement of electrons, a phenomenon called a DD transition that actively paints the vibrant world we see.
Which brings us to Section 2, real-world superpowers, looking way beyond the party.
Because the crucial point here is that coordination compounds are not just abstract laboratory concepts. They are the hidden structural backbone of both biology and global industry. They literally possess real-world superpowers that make life on Earth possible. Remember our very first question about grass and blood? Well, chlorophyll, the essential pigment powering plant photosynthesis and basically the entire global food chain, is just a coordination compound with a magnesium host at its center. Hemoglobin, which diligently carries life-saving oxygen through every single vein in our bodies, is a coordination compound with an iron host. That is exactly why your blood is red. And the miracles don't stop at biology. Vitamin B12 fights pernicious anemia using a vital cobalt host. Moving over to heavy industry, a specialized rhodium complex known as the Wilkinson catalyst drives the hydrogenation of alkenes, which is absolutely critical for manufacturing. And silver and gold complexes? They're used to perfectly electroplate smooth, protective metallic coatings onto everyday articles. It is honestly astonishing how one chemical principle scales all the way from the microscopic cells in a leaf to a massive global industrial factory.
From keeping us alive with every single breath we take, to powering the very base of the global food chain, to building the materials of tomorrow, these tiny, highly organized molecular parties truly run our world. They're the unseen architects of both life and technology. The chemistry of coordination compounds is vast, it's elegant, and it's constantly evolving as we discover new ways to utilize these microscopic superteams. So then next time you look at a green leaf or a brilliantly dyed piece of fabric, remember what's really happening underneath. What chemical superpower will you discover next?